So, greetings. As I promised, I'm trying to make a video about the solutions of the sample test questions uploaded to the CodeSpace. So this year I won't have any test questions for you regarding the K-server problem, because so there will be an available material for the K-server problem, but in this year it won't be a part of the curriculum of this course, but you can read about this if you wish, and there are lecture notes. So first, let us consider the ski rental problem. So the first question is about ski rental. Good. The price of the ski is B equals 8. Okay. What is the optimal deterministic online algorithm for this case, and what its competitive ratio? Now for this, of course, the optimal algorithm, so the optimal deterministic online algorithm, meaning having a best, the smallest absolute competitive ratio, online alg, is A8, which means that it will buy the ski on the 8th snowy day and renting till that time. And what's its competitive ratio? So the competitive ratio is always 2 minus 1 over b, which is 1 over 8 in this case, and that's just 15 over 8. Okay. The second question is, describe the run of the A3 algorithm if the length of the season is n equals 5. So the length of this season is always the number of the snowy days, but I will make this more explicit in the actual test this year. So A3 buys on the 3rd snowy day, which means that the run of the A3 algorithm is just rent, and then it's rent, and then it's buy, and then it's a skip, and then it's a skip for the snowy days, because for the last two, if the length of the season is 5, then it means that we have 5 snowy days for the snowy days. And of course we just skip for the others. And of course, if I'm asking the cost of this algorithm as well, then the rent by is 1 plus 1 plus, well, okay, so it's b equals 8, so the price of the ski is 8, the cost is 10, and of course the optimal cost would be just 5 in this case, so that's already twice as bad as it should be. Cool. Now I will clear these pages as well, and that's all. So basically for the ski rental problem you are just having these sort of questions. So I will give you the price of the ski, and you should talk something about the best possible algorithm, which is always A, B, So that's where the b comes in, and there is a formula for the competitive ratio, but that's all. And of course, for these algorithms, a indexed by this number, in this case is 3, you should know that it means that this algorithm will just buy the ski on the third snowy day and just renting the skis in the previous days, and that's all. Okay, so let's move to the second question, and I'm just having a page here. So we have a matrix game, so we have a coast matrix which is 1, 3, 5 and 2. Okay, and we just have to compute the value of this matrix game. And of course, in these sort of questions, I'm always asking for the optimal mixed strategy, which means that both players have probability distribution as their strategy. So for this case, the value of the game is, say, the maximum for all the possible probability distributions p. So basically the first player will choose the first row with probability p1 and the second row by p2, but since these two probabilities of course sum to 1, this will be 1 minus p, and this will be p by probability p. And if we need this, then the column player will choose the first column by probability q and the other column by probability 1 minus q. So this is just the maximum of the minimum for all the possible probability distributions the other player can have, and we just have a vector times a matrix times a vector product. Transposed, q is transposed, so it's a column vector in this case, which is the same by the Loomis theorem. So you just write this here if you wish. So by the Loomis theorem, it's the same as the maximum for all those probability distributions p and the minimum, but for the minimum we don't have to consider all the possible q's, but only for those j's which are in either 1 and 2, because the column player will play either the first or the second column according to some strategy, some pure strategy, which is the best counter strategy for a fixed p. And we just have to compute this p vector times c times the unit vectors transposed. Now what's this? So basically this is just I'm switching colors, and you can do that if you wish as well. So this is okay, so it's just p and 1 minus p times this 1, 3, 5, 2. So this is the PC part. So this is p. So we just have to compute the okay, so for this cell this will be p plus, and I'm just moving this, p plus 5 times 1 minus p, which is just 5 minus 4p. And for this cell we have 3p plus 2 times 1 minus p, which is just simply 2 plus p. Okay, so we have these two columns, and if we just multiply these by the unit vectors transposed, so multiplying by the 1, 0 would pick this, and multiplying by the 0, 1, multiplying by the 0, 1 would pick that, which means that we have to maximize for the value of p. I'm not writing a vector here because right now I only have one variable, the maximum of p, for choosing the minimum, and this is always the minimum of these entries which we just computed. So it's 5 minus 4p or 2 plus p. And of course p here is a probability, so this is always between 0 and 1. Now you can solve this using a linear programming solver if you wish, but I think it's easy in this case just to draw a graph of these things. So for the value of p, which should be between 0 and 1, for the first one I have 5 minus 4p. These functions are always linear functions, multilinear functions, but if you have only one variable, because it's a 2 times 2 matrix, then this is just an ordinary linear function, so which is 5 at p equals 0, and since minus 4 it will be 1 at p equals 1, and so this is the line for 5 minus 4p's. And for the others it's starting from 2 and it increases till 3, so that's it. So that will be the other line, which is the 2 plus p. So this is the 5 minus 4p. Now the minimum of these two things is just this guy. You can see that they will meet between 0 and 1 because the order changes. So in the beginning, so for p equals 0, the first one, so the lower is the 2 plus p, and on the right hand side of the interval the other gets to be smaller, which means that these two lines meet somewhere in between. And since you have to maximize this red line, you just have to compute this point, which of course happens exactly where 5 minus 4p equals 2 plus p. And if you just do the computations, then it makes 5p equals 3, so p is 0.6. What does it mean? It means that, so the question was compute the optimal mixed strategy for one of the players. We are already done with that, because an optimal strategy for the first player, so for the row player, let's say, it means that you have to pick the first row by a probability of 60% and the second row by a probability of 40%. So it's first row 60% and 40% second row. And the other thing is that and the value of the matrix K, which is exactly this expression, which boils down to the value, with the value is here. So you just have to substitute, say, to 2 plus p, the optimum point. So the value in this game is 2.6, and that's all you should just produce. And of course this is between 2 and 3, because if you remember, there was a Minimax theorem which says that it's always between the minimum of the maximum of the columns. So the maximum of the first column is 5, the maximum of the second column is 3, the minimum must do of these two things is 3. and for these, for the other player, we should just compute the maximum of the minima of the rows. So the minima of this row is 1, the minima of this row is 2, and the maximum of these things are 2. So if you just want to make a sanity check on your result, then you just do this, the minimax operation, the max-min of the rows and the min-max of the columns. You will have, most likely you will have 2 different numbers, and the game's value should fall between these 2 values. And if it does, then you've probably done everything correctly. Okay, so basically that's all you have to do for the second question. If the question is to compute the optimal mixed strategy, and for sure you will get some question resembling to this. You will get a 2 times 2 matrix, and basically that's all what you have to do with the matrix. Of course, it's your choice. If you want to compute the optimal strategy for the other player, that is fine. You just have to compute this for Q and multiply the matrix C times Q from the left, and basically that's all. Now let's see this third problem. So let us consider the paging problem with the cache size, and you should run the algorithm least recently used. Okay, now I won't jump. So you just have to compute the least recently used algorithm for a cache size k equals 3. Okay, so if we just run this algorithm, oh, this is a very long input, but well, initially the cache is empty. Then you will get the first input. I will just highlight this here. So upon reading 1, you will have the 1 in the cache. You are not discarding anybody from the cache. If you wish, you can denote it like this. You are reading a 1 and you are discarding nothing, a 0. Okay, and then you just also add a timestamp. Now I'm also denoting that this move actually cost something to us. And then comes the second input, which is a 2. Since you have a space in the cache, you don't have to discard anything, but since you have to move this guy into the cache, this operation also has some cost. And in this case, you also just write down the timestamp, so it's the second time. Okay, then 1. Okay, since 1 is in the cache, I don't have to discard this guy, so it's free, but still I have to update timestamp, so it's the third moment. I'm just having these 2 objects inside the cache, and then I have this 3 as input. Now 3 is not in the cache, but still I do have space remaining in the cache, which means that currently I will have these 2 guys untouched, and the 3 which came as the 4th request. And of course this operation costs me because 3 was not in the cache previously. Now that's fine, and then this 1 comes. Now if this 1 comes, then again this 1 won't cost me anything, so it's 0, but I have to update the timestamp belonging to this 1, 2, 2, 3, 4, because it was in the 5th moment that this 1 was accessed. Now comes the 4, which is a new guy, and I have to discard something. I have to discard something, and I will discard the 2 because the timestamp belonging to the element 2 is the smallest amongst the 3 guys already in the cache. So amongst 2, 4 and 5, 2 is the lowest, which means that I have to discard that guy, and of course the other timestamps won't change, and 4 becomes a member of the cache at timestamp 6, and then the 2 comes. Now it seems it wasn't that great idea to discard the 2 at this point. Yeah, that might be the case. So you have to discard something because 2 is not in the cache and the cache is full. And in this case, you will discard the 3 because that's the one which was accessed the longest time before. If you just write this down, you are just discarding the 4 when you are just reading the 2 in the cache. And of course for the 2 you just have to add the timestamp which is the current timestamp of the operation. And of course for 4 you don't have to spend anything because 4 is in the cache, but you have to update timestamp belonging to the member 4, so it will be 8. Yeah, that's great. And then you are reading in the 1. The 1 is again okay because the 1 is a member of the cache at this point, so it will get an update timestamp, but that's all what happens to it. And then you are just reading in the 2. That's kind of boring, probably it was randomly generated, but for the 2 it's again free, and then you will just have to update the timestamp belonging to 2 and for 8. Yeah, that's great. And then something happens actually, so it's 3. 3 means that you will have to pay because 3 is not in the cache, and you will discard the 4 because that guy has the smallest timestamp. So this 8 is the minimum, that's why you are discarding the 4, the number 4 from the cache, and it will cost you money. So it's 1, 9, 2, 10, and 3 was read in at the 11th time unit. And then okay, so you are just, let's do this, you are just reading in the 1. You don't have to discard anything because 1 is in the cache, 2 to the 10 and 3 to the 11, that's fine. So only the timestamp gets updated, which is free. And then you just have the 2, which is also in the cache, so it's 2, it's free. Yeah, that's great. So it's 12 and 13 and 11. Yeah, great. Now for reading in the 4, you have to discard someone from the cache, and at this point you will discard the 11 because that's the smallest timestamp, so you will discard the 3, and in this case you will end up by discarding the 3. That's great. So it's 1 and 2 and 4 at time point 14, and then you are just reading the 1. You are just reading the 1 in, but it's free because it's in the cache, so it's 1 15, 2 13 and 3 14. Awesome. And then we have this 4, and the 4 is evicted already from the cache, so we have to eject someone, which will be probably the 2, and then we will have the 1 and the 3 and the 4 inside the cache. I'm not forgetting that this operation actually cost me money, so this guy is not free. And then I'm reading the 2 in, so I will just discard the 3, so it will be 15, 2 at 17 and 4 at 16. Okay, so it was a non-free operation. Yeah, that's great. And then I do have a last value accessed, which is the 3, of course the 3, who else? And I have to evict the 1 from the cache because that guy had the smallest timestamp, which means that it will be 2 at 15, 3 at 18, and 4 at 16, and 4 at 16 as the last operation. Now, okay, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I'm not making any mistakes, then the cost of this algorithm of the least recently used algorithm is 9, for the simple, because there were 9 transitions having a non-zero cost. Not exactly, because I have to denote this guy as well. But of course you will have a round of filling the cache. In this case it was these 3 transitions, and then if you are just evicting or discarding someone from the cache, then you will just see this by having a positive integer as this formal denominator. So the cost of this algorithm is actually 10. Now, there is also a question regarding the optimum value, so compute the value of the optimum as well. And how did you do that? Now, for this, you have to use, for the optimum, you have to use the longest forward distance algorithm. And for the longest forward distance algorithm, I will actually copy this input as well. So it's 1, 2, 1, 3, 1, 4, 2, 4, 1, 2, 3, and then the 1, 2, 4, and then 1, 4, 2, and 3. Yeah, okay. Now the longest forward distance will first fill the cache, which means that till this point only the first 3 elements, so at this point the cache will contain the 1, 2, and the 3. Okay, and this is the point when the algorithm will discard some of them, and then I'm just so far I had a cost of 3. This is the same situation which we had for the least recently used algorithm as well. Now then I'll just have to check, so 2 is accessed here, 1 is accessed there, and 3 is accessed there the very next time, which means that I will need, amongst these guys, I will need 3, the latest, the earliest, so that's why I'm evicting here 3 from the cache, and from this point I will have this 1, 2, and 4. So since this guy was the longest one, but this cache content 1, 2, 4 will be good till this point, right? And then I'm getting the 3, and I just have to check that 1 is accessed here, 2 is accessed there, and 4 is accessed there at the earliest, which means that in this case I will have to evict this 4, which means that the cache, the cache content is at this point is 1, 2, 3, because I have to move the 3 in and I will move the 4 out. But this cache content 1, 2, 3 is enough till this point, okay? And then amongst these 1, 2, 3s, I will need the 3, the latest, which means that I'm just moving out the 3 and moving in the 4. And for this 1, 2, 4, it's enough till this point. And then I'm just, well, since 1, 2, and 4 are, well, none of them is accessed, I can get rid of any of them, and I will just get, say, the 1, 2, 3, which means that I had a cost of 3 in the beginning, and a cost of 1 here, and the cost of 1 there, and the cost of 1 there, and the last cost occurring here as well. So it's just 7. The optimal cost for this particular input is 7, which is computed by the longest forward distance algorithm. And basically that's all what you have to do with the paging problem. Now, most probably you will also have an actual cache size of k equals 3, and most probably you will have to run the least recently used algorithm, another possible candidate being the FIFO algorithm, which is also a k-competitive algorithm, but most probably you will have to run the least recently used algorithm. Good. Okay, now let's see our fourth problem. So the fourth one is now about, what's this about? The scheduling list algorithm for the scheduling problem for unrelated machines, and you will get such an exercise as well. You will have to either for unrelated machines or for related parallel machines, but yeah, that's the two options you will have. And in this case you will have the unrelated machines, which means that here you have m equals 2 machines. Yeah, that's great. I will make drawing as usual, and of course drawing is totally acceptable solution. And then I just have to write down the loads of these two machines. Initially both machines have a load of 0. Now then, this 1,4 means that if I put this job on the first machine, then it will finish in 1 unit of time, and if I schedule this to the second machine, then it will cost 4 units of time there, which means that I have to compare the 0 plus 1 and the 0 plus 4, and of course this 0 plus 1 is smaller, so that's why I'm putting the first job, the 1,4 here. Okay, making the load of the first machine to 1. So it's 1. Now then comes the second input, which is 2, 4. Again, I have to compare this 1 plus 2 and the 0 plus 4. Now this is 3 and the second one is 4, so again 3 is smaller, which means that I will put this 2, 4 here. And of course I will update the actual load of the machines, and of course the first machine's load changes to 3. And then comes again a job with 2, 4, but in this case the 0.4 is only 4, which is smaller than the 3 plus 2, which is 5. So that's why I'm picking this guy here, and it will cost 4 units of time on the second machine. Yeah, that's great. And I'm just updating the loads of the machines, so this guy will have a load of 4. Yeah, that's great. And then I'm having 3, 1. Okay, so comparing 3 plus 3 and 4 plus 1, this is again a smaller value, so 3, 1 gets here. And the updated load of the second machine will be 5. This guy will be 5. Cool. And then I have 2, 1, which means that I will have this guy as the optimal solution, so it's just 2, 1. Okay, so, and the actual load is 5. Now both of the machines are loaded till exactly 5, so this means that the maximum of them, which is the make span, the algorithm's cost The least algorithm's cost is 5 in this case. Okay. Now, what can you say about the optimal value? Okay, so there were actually two bounds. So first, of course, the optimal value is at most 5. That's great. The second, which we know, is that the make span is just the sum of the runtimes of the jobs on the machines, and in this case each of the numbers are integers, so the optimum as well will be an integer. Okay, at most 5, an integer. And of course we have that R star, so the optimum value is always the, well, at least as large as the maximum of the minimum of those Pij's. And for each job, so the maximum possible minimum, so in this case the minimum is, well, for the first job the minimum is 1, for the second job the minimum is 2, for the third job the minimum is 2, for the fourth the minimum is 1, for the fifth the minimum is 1, which means that the maximum of the minima is 2. So in this case this is 2, so the optimum is at least 2. In most cases this is not the best possible optimum, but the second one is that it's also it's lower bounded by the sum of the minima of the Pij's divided by the number of machines, so that's also a general formula for that. And in this case this is just say it's 1 plus 2 is 3, plus 2 is 5, plus 1 6, 7, divided by 2, which is 3.5. So we know that the optimum value is at least 2, we know that the optimum value is at least 3.5, we know that the optimum is at most 5, and we know that this optimum is an integer value, which means that the optimum is either 4 or 5. Now this is enough, of course, if you have to answer such a question, and you can of course try to reach the bound of 4. So you already know how to make make span of 5 here, and you can just make a short case analysis whether the 4 is reachable or not, but it's not really needed. So in this case, if you want to reach the 4, then, well, you have to, well, amongst these three jobs, and you have these 2 jobs. Okay, so these 2 jobs, you cannot put both of them to the first machine because, well, that would be 5, which means that these, or at least one of these guys, will be put on the second machine, which means that none of these 3 guys can be put on the second machine because they would cost 4 and the other 2 cost at least 1. So you should put all those 3 jobs on the first machine, which is again making the make span to be at least 1. So actually, because of this, the optimum is exactly 5, but you don't have to compute this on your input. It's enough and sufficient to just compute the bounds and maybe just say that it's an integer if all the inputs are integer values, and you are just happy with the knowledge that the optimum is somewhere between 4 and 5, and that's all. Okay, so for the next one, I'm having again the scheduling problem, but in this case the scheduling is a timed version, so it's with timestamps, and we just have to run the int_v plus LPT algorithm. Now for this task you will either have to run the int_v plus LPT algorithm, or you will have to run the online LPT algorithm. I believe this is the very same input which is in the lecture notes as well, but let's do this. So for the int_v plus LPT algorithm, we have, say, 3 machines. Yeah, that's great. We have 3 machines, okay. And 0 is the time point when we already have jobs and we have all the machines being idle, which means that, so I'll have access to the job 10, 10, 20, and 30. Remember, the first number is the cost of the job and the second number is the timestamp when the job actually arrives. And whenever we arrive to a time point in which all the machines are idle, they are not doing anything, and we still have jobs which are unprocessed, then we just make an optimal schedule of the already available jobs. For example, in this case, I'm just putting the 3 here, and I'm just putting the 2 there, and I'm just putting the 1s here and there. So if you just have to so this is the int_v algorithm by itself, what I told, an optimal solution. But for the LPT suffix, that's not exactly how you do this. So you have this bunch of the available jobs. You always have to put them in decreasing order according to their cost, and use the list algorithm, the original list algorithm, for scheduling them onto machines. So in this case I have 4 available jobs, that's fine. The largest one amongst these is this 3, so I have to put this on one of the machines. I will put this guy here, 30. Now that's fine. From the remaining jobs, 20 is the largest one, so I have to schedule this on one of the machines according to the list algorithm. The list algorithm will choose the second machine because that would, so you just have to pick the machine which will with the least possible load, and if you have several choices, then you just use the machine with the smallest index. The topmost is machine 1, the second is machine 2, and so on. Then the job 10 will get placed here because that's a job of size 1 and the third machine has the least load, and then you will have this 10 which is also placed on this third machine because that guy has the least load. Okay, and now we just wait till all the machines get empty. Now till that time point, this job will arrive, this job will arrive as well, this job will arrive as well, and this job will arrive as well. I'm just writing these 2, 1, 2, 2, 3, 2, and 1, 3. Okay. Now I just have to again sort these guys into descending order because that's what heroes do, that's what the LPT algorithm does. Longest processing time comes first, so it's the 3, 2 gets placed here. Okay, but this is the point where I'm scheduling, so I will start from here on the other machines as well. So the second, so let's say this guy, 2, 1, can be placed there, and 2, 2 again can be placed here, and the 1, 3 will be placed here because at this point this is the machine with the least possible load. Okay, we just scheduled all of these things, so I'm just waiting till time point 6, and till time point 6 I will have the jobs 2, 4 and 1, 5 arrived, And if I'm just running the LPT int_v plus LPT algorithm, then I will process this guy first because that's the larger amongst these two jumps, 2, 4, and then I will get this 1, 6, 5. Cool. So that's it. The algorithm's cost in this case is the make span, which is 9. Which is 8, sorry, 3 plus 3 plus 8. 3 plus 3 plus 2 is 8. Now great. Okay, so again we'll have what can you say about the optimal value. Now for this it's enough just to consider that the optimum is at least as large, or L star is at least as large as the processing time plus the starting time. So it's just at least as large as the maximum of these values. So amongst these values, these 2 plus 4 or the 1 plus 5 each give you a bound of 6. So in this case L star is at least 6. You can try to optimize, but you don't have to optimize at this point, so it's enough just to write down this solution and move on to the front. And move on. Okay. So let's just run the algorithm MTF, which is move to front on this input. So that's the next task. Move to front on, say, the input sequence 1, 3, 2, 1, 4, 2. Okay, so the move to front algorithm, this is about the list access problem. So this is our initial list, and if we are just accessing the 1, I'm just adding here, so I have to pay 1 because 1 is the first element of the list at this point. And then the move to front algorithm will move the requested element to the front of the list, which doesn't make any difference because 1 is already the first element of the list, so it will have a cost of 1. And the list doesn't change, so it will be 1, 2, 3, and 4. Okay, let's do this. Then, what do I have? There is an access for the element 3. Now for the element 3, first this guy has a cost of 1, 2, 3 because it's the third element in the list at this point. And then the 3 gets moved to the front because that's what the move to front algorithm does. It just moves the currently requested element to the front of the list, and the order of the remaining elements remain the same. Okay, and then comes the request for 2. Now the request for 2 is not a very good one because the 2 just got behind, so it's 1, 2, again a cost of plus 3, which is again pushed to the front, so it will be 2, 3, 1, and 4, the current list, because 2 gets pushed into the front of the list. Next, 1 is accessed. Now 1 being accessed is not necessarily a bad news, and it's not necessarily good news as well, because plus 3, 1, 2, 3 is the third element, and of course I'm moving this guy to the front of the list, and I will get back the initial list 1, 2, 3, and 4. So of course this was not the best possible choice, because for every element we just paid 3, which is more than the optimum, this is for sure. And now I'm accessing the element 4, having, say, 1, 2, 3, 4, a cost of 4, because that's the fourth element in the list, and I'm moving this guy to the front. And then it's 4, 1, 2, 3, and finally I'm accessing the element 2, having a cost of 3, because in the current list that guy is the third one, and then I have to update it to 2, 4, 1 and 3 because the move to front algorithm moves the most recently accessed 2 to the front of the list. Okay, which means that the cost of the algorithm in this case is, well, 1 plus 3 plus 3 plus 3, it's already 10, it's 17. So the cost of the algorithm run on this input is 17. Now, what can I say about the optimal value? So this is a quite hard optimization task. You shouldn't try this at home. But since we know that MTF is too competitive, this means that the optimum is at most 17 over 2, at least 17 over 2, which is 8.5. So the optimum, well, and of course the optimum is an integer because we always pay integer values, so you can just finish your task by stating that the optimum value has a cost of at least 9. And of course, if you are not moving anything, then you will pay 6, 7, 8, 9, 13. So of course, if you are just not moving anything at all, then you can just get that the optimum is at most the sum of the values, which is 13 in this case. Yeah, that's great. And probably you can do better, but it's enough just to do this in your MTF algorithm. You will definitely get one such exercise as well, because the least access problem is also one which is covered by the practice part of this course. And the last one which we covered this day is the bin packing problem. Now for this you will get either the first fit or the next fit or the best fit algorithm, and you will have another one on which you will have to run either the harmonic algorithm or the next fit shelf algorithm. So if the task is to run first fit on this particular input sequence, then it's easy. So it's just for the first bin you are just pushing 0.5, and of course it's enough just to denote this by this. So for 0.6 it won't fit here, so 0.6 gets a new bin. And then 0.3, now since we have the first fit algorithm, you're just pushing this guy into the very first bin in which there is enough space, so 0.4 gets placed here. This bin is full already. 0.2 gets placed here because it fits, and if it fits, it sits. So 0.5, it needs a new bin. And then 0.4, oh yeah, so it fits here, and you just get the value of 3. Now, what can we say about the optimal value? Well, the optimal value is always at least as large as the sum of the size of the items rounded up. So in this case it's just a ceiling of 2.9, which happens to be 3, and since we already have a solution of cost 3, it means that the optimum is exactly 3, so we can say that the optimum is actually 3. Now the second option for this particular problem would be just to run the best fit algorithm for the very same input sequence. So for the best fit, case of the best fit, here if you had those questions, then well, you are just starting up the same way, and then the 0.3 would get placed here because that's the most full bin into which this item fits. And here 0.4, well, it will fit here because that's the most full bin into which the item fits. And then the 0.2, okay, so the 0.2 doesn't fit anywhere into the open bins. And then 0.5, this is also, well, this is the only bin in which there is enough space. And the 0.4, it's too large. It doesn't fit into any of those bins. So in this case, the best fits value will be 4. It's using 4 bins. And for the next possible task, so you will see that in the sample there is the so-called double coverage algorithm, which is for the K-server problem, but you won't have such an exercise in the test, but you will have another one which will be either the next fit shelf algorithm or the harmonic. And for example, if it would be the harmonic algorithm for, say, k equals, say, 3, then you will have a bin for items of size at more than 1/2, and then you would have a bin for items being larger than 1/3, 1/3, but at most 1/2, and then you would have a bin for items of size at most 1/3. And then, okay, so processing this guy, so first this gets placed here, 0.5 to such a bin. 0.6 is larger than 1/2, so it will get placed into a bin for the first category, and then you will get this 0.3. 0.3 is smaller than 1/3, so you will just put this guy here. 0.4 is somewhere between 1/3 and 1/2, and it fits here, so it's fine. And then you will have a 0.2, which is also smaller than 1/3, so you are just putting the 0.2 there. Now 0.5, it fits into the second category. It's between 1/3 and 1/2, because 1/2 is allowing the equality here, but this item doesn't fit here, so you just have to open a new bin for this category. Now, of course, there would be enough space in the category for the very small items, but the harmonic algorithm doesn't do that. It doesn't use space that intelligently. And then you will have this 0.4, which is again an item having a size between 1/3 and 1/2, so it's in the second category, and that's all. So in this case, the harmonic 3's cost is 4 because it uses 4 bins, and basically that would be the solution if you would get the harmonic value. Now for a sample for the next fit shelf algorithm, I think you should just watch the previous video in which I had an example for the example run of the so-called next fit shelf algorithm. And basically that's all. You won't have more tasks, and the task will look almost exactly like this, but maybe it's, in this case, it's either unrelated or parallel or just the simple case. Here it's either int_v plus LPT or the online LPT problem. Here it's either first fit or best fit or next fit maybe. And the next one is, instead of the K-server problem, you will get either the harmonic or the next fit shelf algorithm. You will get a 2x2 matrix for computing the optimal mixing strategy. You will get either LRU or FIFO for the marking problem, but most probably the LRU, and then you will get some warming up example for the ski runner problem. So as I said, 1 hour is sufficient, but you can use your 2.5 hours if you wish to write your tests next week. Okay, so it will be on the 7th of December from 2 p.m. on the CoSpace system. And till then, bye bye.